Let's start the afternoon session. The chair of the first talk is Professor Makiko Tanaka from the Tokyo University of Science.
Thank you very much. Good afternoon, everybody. The first speaker, 大丈夫ですか? The first speaker of this afternoon session, Dr. Tomoki Fujii from Tokyo University of Science. And the title of his talk is Graphical Solitons, Invariant and Hyperpolar Actions. Please start. Thank you.
First, I would like to express my gratitude to organizers for giving the opportunity of this talk. Thank you. So in this talk, we consider the graphical translator and graphical rotating soliton for the mean curvature flow. This is the content of this talk. First section is introduction. In this section, I state the basic fact of mean curvature flow and the soliton, and also state the background of the study of this talk. After that, in 3 sections, I state the result of my study, my research. In the second section, we consider the translator for the mean curvature flow given as the graph of a function on the unit sphere, which is constant on its parametric hypersurface. We classify the shape of such translators. After that, in the third sections, we consider a more general case. That is, we consider the translator given as the graph of a function on the symmetric space, invariant, and isotropy action or cohomogeneity to harm actions. Finally, I state the recent work about the rotating soliton. So let's start. First section is introduction. In this talk, we consider a graphical translator. So the ambient space of mean curvature flow and translator and rotating soliton is a Riemann product of the Riemann manifold and the n-dimensional Euclid space. So let n be n-dimensional Riemann manifold and M be n-dimensional C-infinity manifold. Also, FTTI be the C-infinity family of C-infinity versions of M into n times m-dimensional Euclid space. And denote by MT the image of FT. And AT is the mean curvature vector field of FT. Then we define the mean curvature flow as the flow of images. That is, if FT satisfies these equations, the family of images MTTI is called mean curvature flow. Here, this mark means the normal component of the vector field. Next, we define the X soliton for the mean curvature flow. C-infinity immersion F, C-infinity immersion F, let F be a infinity immersion of M into N times Rm. And gamma is that images. And X be the Chilling vector field on ambient space. Then X and F satisfies these equations. If X and F satisfy this equation, gamma is called X soliton. For the about the X soliton, the mean curvature flow starting from X soliton, soliton follows the one parameter transformation group associated to X. So on the mean curvature flow, X soliton is not change the shape. That is not change that shape. Next, we introduce the special case of X soliton. Let gamma be the X soliton. In the case of M equal 1, that is, the ambient space is the Riemann product of the Riemann manifold and one-dimensional Euclid space. Then, if X, the Chilling vector X is like this, gamma, then gamma is called translator. And in the case of M equal 2, the Chilling vector X satisfies this equation. The X soliton gamma is called rotating soliton. Here, matrix A is like this. In this talk, we consider the translator and rotating soliton. Here, we introduce the example of translator and rotating soliton. First, we introduce translator. Look at this example. This curve is the graph of the function u defined by ux equal minus log cosine x. This graph is a translator, and this translator is called the Grim Reaper. On the mean curvature flow, the Grim Reaper move upward. And the Riemann product of the Grim Reaper and Euclid space is also a translator. This translator is called a Grim hyperplane. Grim hyperplane is like this. And on the mean curvature flow, this Grim hyperplane move upward. And we introduce example rotating soliton. The rotating soliton in two-dimensional Euclid space the existence of rotating soliton of two-dimensional Euclid space is proved. The such rotating soliton is called in-yang curve, and in-yang curve is like this. like this curve. On the mean curvature flow, linear curve moves rotating this direction. Next, we consider the graphical translator. First, we consider this case. So, U is the symmetry function on domain M of N to R. And embedding is graphical embedding. So F is defined by FP equal PUP. And the image of F is the graph of U. Then if U satisfies this equation, these equations, gamma is translator. So this partial differential equation is the condition of translator. The example of graphical translator, we introduce a ball soliton. A ball soliton is the complete translator given as the graph of the rotationally symmetric function U on Rn. Kurtabak-Schunner shows that the ball soliton have this asymptotic expansion as R approaches infinity, where R is the distance function in Rn. Here, the function U is the composition of R and some function V. The graph of the image of ball soliton is like this. This asymptotic expansion is proved like this. Let R be the distance function on Rn. So R is defined by Rx equal norm of x. And U is, and since U is the symmetric rotationally symmetric, so U is composition of R and some function V. And the graph of U is translator. So U satisfies this equation. So U equal VR and this equation, from U equal VR and this equation, V satisfies this ordinary differential equation. Kurtabak-Schunner shows the asymptotic expansion of the ball soliton from analyzing this ordinary differential equation. This analyzing is the this translator is the this translator have the invariance of rotational symmetric. So I consider I consider the translator. I consider the more general invariance case. That is the study of my work. Second section, we consider the graphical translator on the sphere. So we consider the translator gamma given as the graph of the function u, which is constant on the isoparammetric hypersurfaces. So we assume that like this. So let R be the isoparammetric function on N with this. And then U is the composition of R and some function V. So U equal VR and U satisfies this equation. We obtain this proposition. So if V satisfies these ordinary differential equations, gamma is translator. So this equation is the condition of the translator given by the U equal VR. From this equation, we analyzing the shape of the translator given by the graph of U equal VR. So then we consider the case that N is a unit sphere Sn. Then Münchner shows that the isoparammetric function R on Sn satisfies this equation. So alpha and beta is derived. Here, the isoparammetric hypersurface is defined by the level set of R has k distinct principal curvature, lambda 1 and 2, lambda k, with respective multiplicity m1 to mk. And also, k is equal 1, 2, 3, 4, or 6. By あ、電池切れてるかもしれない。はい。これは。By substituting H to this ordinary differential equation and analyzing this equation, we obtain this theorem. So the shape of the graph gamma V is like one of those defined in type 1 to type 5, this 5 type. Where the alpha is alpha, the number alpha is defined like this. And the domain in 0 alpha. This 5 types, this 5 type is similar to the case of the unit sphere. So type 1 is convex downward, and type 2 is increasing, and type 3 is decreasing. And type 4 is the domain of V include the left side, and type 5 is include the domain of V is include right side. So the shape of the graph of V is classified like this 5 pattern. This classification from this classification, the translator given as U equal VR is also classified. Next, we consider this case. We consider the case that N is the higher rank irreducible symmetric space G over K of compact type. And this symmetric space with the homogeneity to Hermann action. And we assume the translator gamma given as the graph of the function U on M of G over K. And this function invariant under the Hermann action, under this Hermann action. Then we assume that this let R equal R1 and R2 be the function, R2 valued function on G over K with G number Ri and number Rj equal canonical delta Ij. And and the level set the orbit of the Hermann action. Then U is a conversion of R and some function V. By substituting U equal VR to this this partial differential equation of U. So we obtain this theorem. So before explaining this theorem, some notation is introduced. Let theta be involution of G with these relations. And R is the maximal abelian subspace of kernel of theta plus identity function. And expo be the exponential map of g over k at O equal ek. And C is the y domain. Also, denote by x the tangent vector field on exponential OC, defined by assigning the mean curvature vector of the orbit HW at W to each W in exponential OC. By identifying exponential OC with C, we regard X as a tangent vector field on C. Then we obtained this theorem. So V satisfy this equation if and only if the graph of U equal VR is the translator. Here, x1, x2 is the Euclidean coordinate of R, and V is regarded as a function on or through x1, x2. And xi are the components of the tangent vector field x on C with respect to the Euclidean coordinate x1, x2 over R. So, x equals the sum of xi ddxi. Here, the component the component xi of the above tangent vector field x is given by Professor Koike. Next, we consider the particular case. So, if gamma number v equal fx for some function f, then we obtain this theorem. So, capital F satisfies this equation if and only if gamma is the translator. This equation is the ordinary differential equation of capital F. So, analyzing this equation, we consider the shape of the graph of F. So, we consider this case. So, in the case that Ham action is the direction of this, the shape of the graph of V point 0 is the classified 5 pattern. Here, x1 and x2 is given as given by Koike like this. And this is the classified classification with the graph of V point 0. This graph is the this graph is the behavior of V on the line x equals 0. The type 1 is the type 1 and type 2 and type 3 are increasing. And type 4 and type 5 is the convex on downward. This is the example of the translator given as the graph of the function invariant under the commutative function. But this graph is the only this graph is only on on the line x equals 0. So x in the case of x is not 0, I not know the behavior of this graph, behavior of the graph of the function v. Finally, fourth section, we consider the rotating soliton for the mean curvature flow. I call the rotating soliton's definition. The rotating soliton is the x soliton defined when the Killing vector x is defined like this. So on the mean curvature flow, the rotating soliton moves the rotating on R2. So then let n be the n-dimensional Riemann manifold. Then we consider the rotating soliton gamma given as the graph of the R2 valued function u equal u1, u2 on M2 R2. And M is the subset, subset of N. Then this the condition of rotating soliton is like this. So U1 and U2 satisfies this equation if and only the graph of gamma, the graph of U is rotating soliton. Where B1 and B2 is defined by like this. V1 equal Laplacian U1 and minus this part, and V2 equal Laplacian U2 minus this part. So then we consider the case that the function U is invariant under the cohomogeneity one action. So we assume that like this. Let R be the function on N with the norm of gradient R equal 1. And that level set is the orbit of the cohomogeneity one action H to N. And U is a composition of this R and the sum function V equal V1, V2 on Rm. This is R2 valued functions. By substituting U equal VR to this equation, this equation calculated to like this. So if the graph of U equal VR is the rotating soliton, V1 and V2 satisfies these ordinary differential equations. Here, HS is the mean curvature of the principal orbit R inverse S of the conformity one action H to N. From these equations, we analyze the shape of the translator given as graph of the function of U equal VR, but I don't have I don't have no result about the shape. So about the rotating soliton is the recent work of the rotating soliton is the recent work of the rotating soliton is this lemma and this proportion only. So this talk, my talk is finished. Difference of this talk is like this. Thank you for your attention.
Thank you very much. Are there any questions or comments?
So please show me the your first result about translating soliton. Pictures or first theorem. Okay. So is it possible to study the asymptotic behavior of the graph of V? So what's the growth rate of such a graph?
Now, I don't know the domain of the both sides of the domain of V. So it is complicated the growth to calculations of growth.
Kurtabach-Schulz-Schurner's result, their soliton grows quadratically, the quadratic growth. But in your case, it is complicated. Is it complicated to calculate? Okay.
No, yeah. So, yes, this case is complicated.
Are there any other questions or comments? Are there any questions or comments from participants from Zoom? 大丈夫か。Can I ask one question? Why did you consider the cohomogeneity 2 hammer action? Cohomogeneity 1 hammer action, that case is already no?
Now, first I consider the isotropy action, and so more general to generalize, we consider the as we consider the rank 1 symmetric space with the isotropy action, and so to generalize, we consider the rank is higher. So and then we know the result of Koike. So we use this type.
Okay, thank you. Are there any questions or comments? Okay, let's thank the speaker again.